Welcome to this section of end-to-end machine learning project. In this section, I would like to discuss some of the code that comes along with the textbook for this chapter. And the idea is to go through some of the major steps, and you could go through the whole code on your own as well. First of all, you should be aware that there's a GitHub page that's associated with a book, and then it's in this link, which is specified in the slide and the textbook as well. You should get a whole copy of this on your own computer, and then go through each one of this as time goes on. By now, you should have already finished 0-1 machine learning landscape, and then you should be reading through 0-2 end-to-end machine learning project. Let's take a quick look of the project, of the code. So you can see here, first thing you want to make sure you have all the libraries that's needed, and also set up the proper directory that you want to see if some of the output from this code. Set up, and then get the data. From the get the data, you can see here what it's trying to do is calling this fetch housing data function, which is defined right here. It's based on a URL on the on the GitHub. So you could always just change some of this path into your local path so that you make this process slightly faster when you run through the whole thing. So going forward, if you do that, it might save you some time. And then you load the housing data. Load the housing data is a function that I wrote here, but essentially is trying to specify the path and then read that CSV. And once you have that data, you can look at the data itself. What do we call it? More like descriptive statistics analysis. So you do this, look at the head of the data, what you should pay attention to, what would be the columns or variables of this data frame. So here, for example, housing median age, total rooms. So here is very interesting. Here you should be aware this total rooms is a big number. So what does that indicate? This indicates this is probably not for individual houses. It's probably for, as we said in the textbook, it says the block, the census block of a particular area. And then the total rooms, population, number of households, there we go. And then you got median income and median house value and ocean proximity. For median income, so here you should go back to think, okay, what's this unit? Turns out to be thousands. So it could be here essentially 8,000. A lot of data later, if you look at the histogram, you would realize it lives in somewhere around 30,000, 40,000. And then we also discussed potentially you could come back with derived variables. Let's think about what can it be. One of them could be total bedroom divided by number of households. You can come back with bedroom per household. Or use total rooms divided by household, number of rooms per household. Or you could think about total rooms divided by population. Per unit of population, how many rooms that they occupy. With the idea that, okay, why this would be impacting my house value. With the idea that potentially, if one person is occupying 3 rooms or 2 rooms or 1.5 rooms, probably would be in a wealthier area that have to pay more to the house. But this is really just some sort of assumption or conjecture, but at least you could test it out in your model. Here, just give you some examples, not necessarily meaning you should try that. So I'm throwing out some of the thoughts, here for this data set so that you could think about what you can do with your own data set. Okay, let's look at house info. House.info essentially tells you the structure of the data, which gives you the type of each of the variable. Let's look at one of them, total bedrooms. Here it has none now of this many, and it's a float. And then if you look at the total number of observations, it's really more than this number. Essentially tells us there are some now values for this variable for whatever reason. So we discussed potentially you could think about what to do with these NAs because it would impact your results. And then we discussed you could fill the NA with a median or mean. You could omit this variable. You could omit the observations that are NA, and then you could infer from other variables. Infer essentially tells you that suppose you have a variable of total rooms, you figure that there's some relationship between total rooms versus total bedrooms. So you could infer based on this variable on some of the not available cells for this variable. Just to give you some general sense. And then here, you can use value underscore counts to look at the distribution, describe to look at distribution for each one of the dimension, numeric dimension, and give you another example, median house income, this many observations, that's a mean, standard deviation, minimum, 25 percentile. So it's pretty much you would be able to see the distribution. Then we could leverage histogram to look at each dimension, numeric dimension, how the distribution look like. Just pay attention to here that you have to specify number of bins. You should test that out with different bins, how the chart look. The idea is you cannot be having too less bins, so you don't know the exact distribution, but you cannot have too many bins, which make your graph is hard to understand. Now, we mentioned that you need to take out a test data set. Here it essentially tells you you could use a random seed so that it would make this notebook's output identical at every run for the test set. So if you implement this random.seed, you are able to make sure your test indices does not change when you run this shuffled indices. Of course, here when we do the split, it's used 20% as a split ratio. Turns out this would be our training for 80% and test for 20%. So here it's just something that's just test check to to check if your test set actually indeed didn't change. So you can read through this. It's very rigorous, right? You really want to make sure your test doesn't change, test set doesn't change. Now here has a more slower version of that implementation. I'll go through some of this. Now, just give you a sense on what that is on the test set. You could also leverage this train test split directly using the dataset, test size percentage, random state to give you a set. This one actually is the easiest one for you to use because it's already will be able to make sure the test set is not going to change when you run through this one more time. Essentially, scikit-learn, this function train test underscore split, has done the job for you. So in this section, in here, it's really trying to tell you how to implement stratified sampling. So idea is really that in case you know your distribution, you want to make sure that your training set percentage for this category should be representative among the whole population. In other words, in the whole population, if this percentage only accounts for 20%, you want to make sure in your training data set, this category only have 20% as well. Okay, it's called stratified shuffle split. And then here is just testing to make sure it is indeed doing a better job than the original random sampling approach. Same thing, just do the comparison. Okay, next section we want to look at discover and visualize the data to gain insights. So here plot a scatter plot with x being longitude, y being latitude, and then you can save the figure. And then you can adjust the size based on adjust the size of the points so that you would be able to see there are more observation here. And then you could also even just use what we saw in the slides using the median house value to represent the expensiveness of each area. You could do the same thing and then have a background map with a with the median house value as well. That's further enhancement of the visualization, basically. Now let's look at this correlation matrix, which is housing.corre, which is a correlation. And then you use median house value to run a correlation matrix with the rest of the variables. We discussed this graph, for example, median income has a positive correlation with the median house value. Now you can further even take a look at this chart. And then here tells you how you can define new variables, potentially. And then later you can test on these variables, of course, in your model. That's the whole purpose of doing this. Here are some more charts. This part, we call it prepare the data for machine learning algorithms. Specifically, I mentioned that it's really just trying to automate some of these data preparation processes. Looking at the NAs. Housing that is now. So look at the NAs. Turns out only the total bedroom has NAs, remember, right? But in your data, there's a chance that more variables may have NA. Then a couple of options, as we mentioned, drop only the NA observations, drop the whole column. Total bedroom is no longer there. And median, or fill NA with median. And should have fill NA with mean as well. Or here has a function called simple imputer to help you to do the same thing as this fill NA with median. Okay, here actually I don't really want to continue with this section. You should go through on your own. Then let's see. It also gives you some sort of encoder to make sure the relationship among the categorical variables are in line. Here. For in order to automate some of this process of defining new variables or align the relationship among categorical variables, trying to use a column transformer from scikit-learn to help you with this automation. And then last thing that we discussed was you could use a min-max transformation to make sure it's transformed. Okay. So that's a data preparation stage. And the next one we want to look at how potentially you can select and train a model. As we discussed linear regression, you could just fit housing prepared data with housing labels being the dependent variable. Let me see what is housing labels. Let me see. So housing labels itself is the actual median house value, which is a y in your prediction model. So as I just mentioned, which is the dependent variable in your linear regression model. So you use this housing prepared, your data, to fit the linear regression, use housing labels being the dependent variable. Next section, just want to look at how the prediction look like. So you can leverage predict some data prepared to look at the prediction values. And then you want to look at this prediction comparing with your housing labels. You can see the closeness of the prediction, or some of them are not that close, but at least you're able to see that. Remember, we discussed IMSE, root mean squared error, and MAE, mean absolute error, to measure the effectiveness of the prediction of the whole data sets, rather than looking at this just for a couple of them. But still, it's a good opportunity to see, to visualize how good or whether it's working, right? If your prediction is 20 versus 286,000, you know something might not be working that great. Now, right there, mean squared error and mean absolute error. Now, here is a second method. We didn't discuss much, but here is at least you can know you could leverage decision tree here. We're going to go discuss what is exactly decision tree in coming weeks, in a couple of weeks. So don't worry about it for now, but you should you should definitely would know later. Fit the decision tree, and then using that fit decision tree to predict, and then look at your IMSE. Just interestingly, it turns out to be 0, right? It's a good thing, not necessarily. Remember, we're talking about the balance between bias and variance. Okay, we will come back with this discussion more later on. Let's look at how to fine-tune your model. You could leverage cross-validation, which try to balance between variance and bias to pick the best model. And then the last model here tested is a random forest, which is built upon decision tree models to avoid the case of overfitting. Overfitting, you have a 0 IMSE, it's indication of overfitting. Now, if you don't know what is overfitting, you should do some research on your own, but the idea is really the model fits your data so well in your training set that it fit each individual point perfectly, which is not something we kind of wanted at all, because this type of model would have issues with generalization. Okay, random forest IMSE, and then cross-validation using random forest. And one more approach here says using support vector machine. Another algorithm that we're going to learn in one of the chapters down the road, and then it has a grid search that you leverage to search the hyperparameters. And just want to pay attention to this section of the code, because the homework that asks you to do would be based upon some of the code here. And then after that grid search, you find the best parameter, and then you want to leverage the best parameter to look at how is it doing. There's also a function called randomized search, which is not grid search. It's just randomly search those two hyperparameters, number of estimators, and max features. Yeah, based on the grid search best estimator, look at your IMSE. And then for this IMSE, if you look at this 47,000 comparing what we saw earlier, 111,000, that's support vector regression actually, SVR for random forest, which is higher, right? But at least you get a sense that why we are balancing between all of them, not necessarily just the lowest. And then maybe I just want to show you 68,000 for linear regression. So now if we continue to go through here, that's the final model we picked. And you could also compute 95% confidence interval for this IMSE in the test set. So pay attention to which part we're looking at test set, which part we're looking at training set. So far, I think everything, a lot of stuff, if, for example, if you want to predict, you want to look at your test set. If you build a model, you want to look at your training set. Yep, that's pretty much the whole idea of this end-to-end machine learning project. I think you should go through this on your own, more like in a line by line fashion, so that you definitely get a good understanding of it. If you have any questions on this, including the theory or what it's trying to do for a specific chunk of the code, definitely reach out to me. And then there's some extra material on the full pipeline, which I'm not going to go through here. Okay. This actually concludes our discussion on end-to-end machine learning project. And I'll see you in next lecture. Thank you.